Hello, AP Calculus AB, and welcome back to our Topic 6, Applications of Integration. Today is actually a really nice continuation of what we started last semester. You might remember that last semester we were working with particle motion, and we said our particle is either going to be moving along the x-axis, so horizontally, and a lot of times if it was moving horizontally, we said that we were going to have some sort of function of t where it's x of t, and then the particle could also be moving vertically, and vertically we would say our function is y of t. Together that's known as our rectilinear motion, and if you need some refreshing, go back to topic 4 and rewatch those videos on particle motion. Today, though, it should make sense that since now we know our integration, we're going to see how integration helps us with particle motion. So let's do a bit of review. There are 3 review questions at the beginning. Why don't you guys go through those, and then once you're done, you can unpause and see how you did. Ready, set, go. Alright, hopefully things went alright. The first thing you need to remember is that speed is the absolute value of velocity. Sometimes we call it the magnitude of velocity if you're in physics. If velocity and acceleration have the same sign, because remember, velocity not only tells us how fast something is moving, it tells us the direction that particle is moving. And if the velocity has the same sign as acceleration, let's say they're both positive, so you're moving to the right and accelerating to the right, then we say that speed is increasing. However, the opposite is true. If velocity and acceleration are opposite in sign, then our speed is decreasing. Now, there are 3 ways that we're going to be using an integral in particle motion, and they're pretty similar, so you're definitely going to want to be careful with these 3. Okay? The first is using an indefinite integral to find the antiderivative of velocity, right? There's no limits of integration here. Okay? And so if we do the antiderivative of v of t, then we call this an indefinite integral. If you think about the order of our velocity, acceleration, and position of a particle, we should remember, and you can jot this down over on the side, that if, let's say, we're dealing with motion along the x-axis, then x of t would discuss the position. The derivative of x of t is velocity, and the derivative of velocity is acceleration, right? So we kind of have these 3 rungs, and to move down this ladder, you are taking the derivative each time. But if you wanted to move back up, if you had acceleration and you wanted to move up to velocity, that is an antiderivative. And same thing, velocity to position, antiderivative. And so, when we do the antiderivative of velocity here, it will give you an expression for position at some time t. However, don't forget that you will have a constant, or maybe you could say a plus c, because there are no limits of integration, and you might have to find that value of c, which is doable if they tell you something else about your particle. Maybe they tell you where it was located at a specific time, and you can plug in that value to determine the value of c. The second type of integral we see in particle motion is a definite integral, one with 2 limits of integration here. And so the answer will be a value or a number. Now, that number is a little tricky. So I think maybe to best understand it, we need to realize that if we do, and I'll just take the space up here, if we do the antiderivative of v of t, we discussed this, here's our fundamental theorem of calculus, it becomes, we'll say x of t, could be y of t, from time 1 to time 2. And then we have to substitute in each of those values. So x of, or the position of, the ending time minus, fundamental theorem, the position of the beginning time. Well, if you end up at 10 feet to the right, but you started at 2 feet to the right, then what would 10 minus 2 tell us? Well, it would give us an answer of 8, which isn't where you're currently located, but it's rather the distance that you traveled from 2 to 10. But that actually gets a little bit confusing, so we're going to be a little bit more specific about this. So this number is going to represent the change in position over our time interval. Okay? This change in position is often known as displacement. It shows you how far you ended up from where you started. So if you started at 2 and ended at 10, you were displaced by 8 units. Or you could think of it as now you are 8 units to the right of where you started. This answer can also be positive or negative, depending on if the particle lands to the right or the left of its position. However, I said this can get a little tricky though, because we really don't want to call 8 the total distance that we traveled, right? Maybe we can picture a number line really quickly and we can take you on an adventure through time and position. So this is going to show us where our particle is located. Let's say we have 0 and let's make 10 go over here, something like that. So maybe this is 11 and 12, and here is 2. All right, let's say that when we start observing where this particle is, it's located at a position of 2, where we're saying it's 2 units to the right of the origin. And then we watch the particle over some amount of time. And so let's say that the particle moves a few units to the right over here, and then the particle moves back to 0, and then it moves over here, and then it moves over here, and then finally it moves all the way over here and comes to rest at 10. Well, would it be correct to say that the particle only moved 8 units? Well, certainly not, because we would need to take into account all the different lefts and rights that the particle went. Maybe here, maybe let's say that this is 6, maybe it moved 4 units here, but then it moved another 6 units backwards, and then it moved another 6 units forwards, and then it went back again and forward, and so on and so forth, and eventually ending up at 10 means we were displaced 8 units from where we started. But it does not tell us the total distance traveled. The total distance traveled would have to be the sum of all of these different motions to the right and to the left. Or maybe another way to look at this would be if we had that graph of velocity, right? And so we're still going to look from a starting time to an ending time of the graph of velocity, because we've discussed before that 2 ways we have to evaluate a definite integral is to take the antiderivative and use the fundamental theorem, but we could also look at a graph, and hopefully you remember that a definite integral measures the area between a graph and the x-axis. So, and actually I should have drawn this further down, and you can totally skip this part if you'd like and just take a look at our screen. This is more of an understanding of what's happening as opposed to something you'll need to use. So let's say that we have a starting time value here and an ending time value over here, and we're going to graph velocity. And we'll say that our graph goes up, down, and up. Okay? Well, if I'm going to measure the area beneath this curve, then we'll probably need to actually know the areas, and so I'm going to make them up. So let's say this is an area of 5. Okay? And then down here we have an area of, I don't know, let's call this 3. And then last but not least, I have an area of, we'll just go with 1. Stick with those odds. All right. Well, if I were to measure the area here, then we should be able to see that the area would be positive 5 minus 3 plus 1. And so when we do all the math, 5 minus 3 is 2. 2 plus 1 gets us 3. This answer, because it's the answer to the definite integral, is the displacement. What this is telling us is wherever the particle moves, it's going to end up 3 units to the right of where it started. Well, how do we interpret all the individual areas here? These areas are where the particle is moving. So if we wanted to discuss the path of this particle, this 5 right here means we move 5 units right. But then this 3 down below means we move 3 units left. And then at the very end, we now move 1 unit right. Right? The areas are the answers to our definite integrals, and because the definite integral of velocity will tell us about position, they're telling us the position that the particle is moving around to. All right, well, if this is going to tell us displacement, do you have any idea how we could find the total of all three of these without having this negative in here? Because wouldn't the total then tell us the total distance the particle traveled, right? If you moved 5 to the right, that's 5 total steps, and then 3 back, that's 3 more steps. Now we're at 8, plus 1 more is 9. But if we use an integral to measure this, we have a negative. So does anyone remember what we could do to change this so that all of our negatives become positives? What sign in math turns every negative to a positive? And hopefully you're thinking, oh, I do know that. That is, of course, absolute value. And so when we find the definite integral of the absolute value of velocity, it is still a definite integral, as said. Okay? The answer will be a number. But this number is going to represent the total distance traveled by the particle. And so the answer should always be what? Oh yeah, the answer should always be positive. We have absolute value, and since an integral is measuring area, do you remember what happens when you apply absolute value to a graph? And I'll do this graph let's do it in purple. It's going to look exactly the same here, but as soon as I get to the x-axis, instead of going negative, this region of 3 is going to pop up here. Guess I should make that look smaller than 5, huh? And then it's going to keep tracing the positive part. And so this purple graph that I just did is representative of the absolute value of velocity. And now the integral of the absolute value from time 1 to time 2 would add up those 3 positive areas. 3 integrals you need to keep track of are indefinite integral and 2 different definite integrals, one for total distance, one for displacement. And don't worry, we're going to put numbers and actual real-world situations on these. This is applications of integration after a while, but it's important to go through and get our basics down first. There's only one more thing we're going to need for today, and then I have 3 sample problems for you. And that one other theme is manipulating this fundamental theorem of calculus. This is a very, very common technique. So let's look at this. We should know the fundamental theorem of calculus part 1 by now, right? If you're asked to take the antiderivative of lowercase f of x, it is capital F of x from a to b. And then as we continue out, we should probably just know that that is capital F of b minus capital F of a. A very common question, especially with particle motion, is they are going to give you a value of the original function. They're going to tell you something about where the particle was originally. A lot of times this is known as an initial condition or an initial value problem. And then they're going to say, well, if the particle started at a position of 4, where is the particle now? And so they're going to give you one part of the fundamental theorem and ask you about the other. And there are 2 ways that you can solve this problem. We're going to look at both of those too. But before we do that, because we're going to be given one piece and we want to isolate the other, we need to realize that we can manipulate the different terms of the fundamental theorem to give us what we need to be successful. So let's take a look. If we have the fundamental theorem of calculus, and I'm going to rewrite this one more time, a to b f of x dx equals capital F of b minus capital F of a, and they want us to tell them something about capital F of a, we might want to isolate that. And to isolate it, I'm not only going to add, right, equal sign so I can perform algebra, I'm not only going to add f of a to each side, but then f of a wouldn't be isolated. I'm also going to subtract the integral from each side to give us the expression capital F of a equals, f of b hasn't moved, minus the integral from a to b of f of x dx. Now I certainly do not have that memorized. It's very, very easy to start with this, think about the information that you have, and think about what they're asking you to find, and then isolate one of these two terms, right? It just took us one step. Maybe even easier is if they asked us to isolate capital F of b, we'll do the same thing again, right? We have that integral from a to b of f of x dx equals capital F of b minus capital F of a. Then to isolate f of b, I think we just need to get rid of this f of a that's on the right side. And so that's going to give us capital F of b equals capital F of a plus, and then the integral from a to b of f of x dx. We're going to have a different interpretation of what this means later on today, but for now, if you just want to treat it as a formula, that is not a bad thing. Okay, so how does this work? Well, let's say that we're given the equation f of x equals 2x, and we also know that capital F of 3 equals negative 1, and you are asked to find capital F of 1. Right? So we know the equation for the slope, and they gave us an initial condition about the antiderivative, and they want to know something else. Well, two ways to do this. Okay? Option one is we can use an indefinite integral. So we go through and we're going to say, well, I would like to find the equation for capital F of x. All right, great. To do that, that's going to be the antiderivative of lowercase f of x, right? Capital F of x equals that. Cool. So capital F of x will equal the antiderivative of, what is our equation? Oh, it's 2x here. Okay, so capital F of x will be the antiderivative of 2x, which is x squared, plus c. However, we have enough information to solve for c. We did this in our last unit, so in order to solve for c, and I'll maybe do a little divider here, we know that when we input 3, we get an output of negative 1, and so that's going to give us negative 1 equals 3 squared plus c. Solving, negative 1 equals 9 plus c, it looks like negative 10 equals c. And now we have a fully updated and relevant capital F of x formula, x squared minus 10. Once we have that formula that meets that initial condition, now we can actually solve for capital F of 1. Capital F of 1 just means replace the x with 1. It looks like we get 1 minus 10, so f of 1 ends up equaling negative 9. And there we go. We have seen this process before. It's nothing too new. I think in the past we probably stopped with finding the equation. We didn't have to evaluate something else in that equation. But either way, nothing too crazy. But let's see how it can be done using the fundamental theorem. Well, we are going to start with the x values that they gave us. Those are inputs, and we know if we do an integral, the inputs are essentially the limits of integration. So we are going to find the integral from 1 to 3. Of what? Well, of lowercase f of x dx. And we know that when we do that, and that's our setup every time, we know that when we do that, using our knowledge of the fundamental theorem, that it becomes capital F of 3 minus capital F of 1. How does that help us? Well, I see 3 terms here, 1, 2, and 3. Which of those terms are we interested in finding the value for? Oh yeah, we want to find f of 1. So working with this formula, even though it's a little vague, let's isolate f of 1. I'm going to do that by adding f of 1 to the left side and subtracting the integral from the right. So that gives us the value of f of 1 is found by doing the value of f of 3 minus the integral from 1 to 3, and I'll replace lowercase f of x with 2x at this point, dx. Great. Now, all we have to do is determine all the values of the numbers on this side, and we're done. So f of 1 equals, they gave us the value of f of 3, that's negative 1, minus, and then this is just an antiderivative, x squared from 1 to 3. So capital F of 1 equals negative 1 minus, then it looks like we have 3 squared, which is 9, 1 squared, which is 1. Distributing that negative, negative 1 minus 9 plus 1 leaves us with a value of negative 9. And you'll find that although you might be partial to just saying, oh, I just like solving for C, that's very exciting, and that's a good way to go, the advantage to doing it this way is you don't need to be able to find the antiderivative by hand. Because remember what we learned last class? Our calculator can find that value. So the AP exam is very fond of giving you equations where you can't find the antiderivative by hand. You have to do this on your calculator, and then you can combine these together to get the final answer. If you can find the antiderivative and you don't have a calculator, then sure, this method is awesome. But for today, I'm going to focus on this method, both because I think the interpretation is important and also because it's something you will have to use at some point on your graphing calculator. Very common on the multiple choice and the free response. Now that we've gone through all the basics, let's go ahead and take a look at 3 example problems. Keeping with the theme of calculus, we are going to gnaw on these problems. You could argue that they all fit that W, that written portion, or that word problem portion, but we're going to look at 3, where 1 is graphical, 1 is algebraic or uses an equation, and 1 is numerical. It uses a table. Those are the 3 main formats you should expect to see from problems on the AP exam. All of them are going to give you our velocity equation, right? Given a graph of v of t, given an equation, they say rate of change, r of t, it's like a v of t equation, and given a table, and this table gives us both v of t and a of t. Now, why do you suppose all of these give us v of t, or the velocity? Well, we have that same ladder or that tier system where if v of t is the velocity, taking the antiderivative will give us position, and taking the derivative gives us acceleration. They are always going to give you velocity because velocity is the derivative, and this is a calculus class. If this were an Algebra 2 class, they might give you position and ask you questions about that, but you should almost always expect them to give you a derivative equation, which in terms of particle motion is always the velocity. So let's go ahead and get started. The graph to the right shows the velocity of a particle moving along the x-axis, so our position function is probably x of t then, moving along the x-axis from 0 to 11. It consists of a semicircle, 2 line segments, and we should actually assume that this connects over here. The graphing software I used just didn't connect that either way, and 2 line segments. Use the graph and your knowledge of particle motion to answer the following questions. So what you really should do here is you should try these questions and then unpause and come back to me to see how you did. Right? Graph of velocity, it's going to put everything together we've done so far in a nice application of both integration and derivatives. So go ahead and try that first question, and then unpause when you're ready. Ready, set, go. All right. First problem, and I'm just going to run through all of these, but you should pause after each one. They ask, when is the speed of the particle the greatest? Now, we do need to remember that speed is found by looking at the absolute value of velocity. So giving you a couple examples, this is the velocity graph. The y values on this graph are velocity. So if I wanted to interpret this point right here, which is 2, 2, this means at a time of 2, the velocity of the particle is 2. Now the velocity being 2 means the particle is moving to the right at a speed of 2. So the speed at 2 is 2. If I wanted to look at another one, like let's say this point over here, this is 10, 0, this means at a time of 10, the particle has a speed or velocity of 0. The particle is not moving. What is the largest speed? Well, it actually turns out to be this guy down at the bottom. This is 8, -6, which means at a time of 8, the velocity is -6, which means our particle is moving to the left at a speed of 6. And so when we say speed is the absolute value of velocity, I probably wouldn't do that on this problem, but it is possible to graph the absolute value of this equation. It looks something like this, and then it would come back down here, and then go over here, right? The absolute value. Now looking at this, where is the graph at its highest point? Well, it's at its highest point at 8, and it has a speed of 6. Okay, how do we justify that? Well, they didn't even ask you to justify, did they? So at what time is the speed of the particle the greatest? We'd say at t equals 8, the speed is 6. Great. Question 2. At which of the times t equals 2, 6, or 9 is the acceleration the greatest? Well, if we're looking at acceleration here, we need to remember we have the graph of velocity. So how do we create or determine values of acceleration? Well, acceleration is the derivative of velocity, which means if we take the derivative of this, or if we want to know things about the derivative, we should look at what on the graph? Oh yeah, we should look at the slopes. The derivative always measures the slopes of this graph. So let's look at those 3 values that they gave us, 2, 6, and 9, and think about slopes. Here is 2, 6, and 9. Well, looking at this point, if I wanted to find a prime of 2, we'd think about the slope that's right there. That's a flat point. That slope is 0, not a prime, sorry. V prime of 2 is 0, which means the acceleration at 2 is 0. The particle is not accelerating at 2. This acceleration, so a of 6, because this line is going in a downwards direction, is clearly negative. You could count the slope if you wanted to be specific. And this last point, a of 9, is positive because our graph is increasing. So which one is greatest? Explain your answer. Well, I would probably just give all of the values. We would say something like, this is important to explain how you're finding acceleration, and then we just say that a of 2 is 0. A of 6, I guess I should find that slope, goes down 3 over 2, so is negative 3 halves. And a of 9 is, well, we go up 3 and over 1, so is 3. Which one's the greatest? That's the greatest. Go us. Over what time intervals is the particle moving to the left? Explain your answer. Well, we do need to remember that in order, or the function that controls the movement of the particle is the velocity function. So we would say something like the particle moves left when velocity is less than 0. All right, well, how do we visually see where velocity is less than 0? Velocity is the y values. The y values are less than 0 below the x-axis. So I think the velocity is less than 0 on that interval right there. Every y value on that red portion of the graph is where the velocity is less than 0. Okay, so how do we answer this? We say the particle moves left. Let's do some time intervals on 4 less than or equal to t less than or equal to 10. Remember, you can include the endpoints or not include the endpoints. They don't care because v of t is less than 0. Great. 4. Over what time intervals is the speed of the particle decreasing? Now this one can be a little bit trickier. Speed increasing or decreasing takes into account both velocity and acceleration. So one way I like to look at this is to quickly make a double sign chart for both velocity and acceleration. This is a nice reminder of how to make a sign chart too. We're going to start with v of t, and we're going to look at the graph of v of t and ask ourselves 2 questions. Question 1, looking at the graph of v of t, is there any place where the graph doesn't exist? And that would be if there's a gap anywhere. And no, there's not. It is continuous everywhere. V of t exists everywhere. But then the second question is there a space on the graph where v of t equals 0? And yeah, there are actually a few of them. The beginning, at 4, and at 10. So we start at 0, we're going to 11. At 10, v of t is 0, and at 4, v of t is 0. Then we go through and we put in the signs. Between 0 and 4, v of t, the outputs are all positive numbers. They're positive y values. Then from 4 to 10, we are negative. From 10 to 11, we're positive. Second part, we look at the acceleration. The acceleration are the slopes. So same question, where are the slopes non-existent or 0? Well, the slope is 0 at exactly one spot at 2 because that's a flat space on the curve. So at 2, a of t, the slope of the graph, is 0. There are no other places where the slope is 0, but there are 2 spaces where the slope or the derivative does not exist. Those occur at sharp points. We can see 2 sharp points on here at 4 and at 8. So at 4 we have a does not exist, and at 8 we have a does not exist. Looking good so far. Now let's measure all the slopes. From 0 to 2, the graph is increasing, so the slope is positive. From 2 to 4, our slope is negative. Then, from 4 to 8, our slope is still negative. We're going down. And from 8 to 11, we are positive. Okay, well, how does that help? Well, speed of a particle is decreasing when the velocity and the acceleration have opposite signs. So, for example, on the interval from 0 to 2, velocity and acceleration are both positive. But from 2 to 4, they have opposite signs. And I think from 8 to 10, they also have opposite signs. All right, how do we write this? Well, we would say that the speed is decreasing, feel free to abbreviate, on, and then we'd say 2 to 4 and 8 to 10, because v of t and a of t have opposite signs on that interval. You could maybe argue that it would be safer in, interval spelling strikes again. You could argue that maybe it would be safer to say v prime of t equals a of t have opposite signs because they didn't give you the graph of a. However, I did also state up here that v prime equals a of t, and they'd use that later on, so just something to think about. Okay. Now, the question sometimes comes up, could you have seen that from the graph? And the answer is yes, right? You'll notice that those intervals we just found, right? And let's highlight those, 2 to 4 and 8 to 10. Here's 2 to 4. If I would go in the right color, that would be swell. Here's 2 to 4, and then here is 8 to 10. Well, what's happening on those intervals? Well, notice those are the intervals where our velocity function is approaching the x-axis. All 3 other intervals, the graph is going away from the x, away from the x, and away from the x. And so if you're going away from the x, that's an indication your speed is increasing. Going towards the x-axis is decreasing. But I think it's much easier to talk about the opposite signs than discussing where the graph is approaching the axis and why that means our speed is increasing or decreasing. Okay, next up. Find the total distance traveled by the particle over the time interval 0 to 11. All right, well, total distance traveled, I think that has to do with the integral of velocity, and you can check that first page. And we don't have an equation for this, so I think the integral of velocity means the area underneath the curve. So let's at least find all the areas, and then we'll talk about the weird negatives versus positives. Right? My first area down here from 0 to 4, this is a semicircle, so it's going to be half of pi times our radius squared. Our radius is from 2 to 4, it looks like, is 2. Okay, my next one is this piece in red over here, right? This triangle. It has a base of 1, 2, 3, 4, 5, 6. 1/2 the base, and then it has a height. We always draw from the base a perpendicular piece to the tallest or shortest part, I guess, of the triangle here. So 1, 2, 3, 4, 5, 6, and a base of 6 as well. Cool. And then we have one more triangle, and people always miss this one. It's this little triangle that's at the end right here. Base of 1, height of 3. So 1/2 times the base of 1 and the height of 3. All right. Now, how do we use those to help us solve the problem? Well, total distance traveled. If we were to add up the three areas that are here, this would be positive, this negative, and this positive, above, below, above. But total distance traveled, we need to remember that the areas underneath each of these are like the distance the particle moves from wherever it started. So this yellow area is going to move the particle to the right. And then the red area is going to move it to the left. It's going to cancel out some of this. And then the purple area is going to move to the right again. We don't want any of the areas to cancel out. We want them all to be positive so we can add all of them up. And so the way that we do that is we set up the integral from 0 to 11, but we say we only want all the areas to be positive, so we do the absolute value of our velocity graph. And the absolute value of that graph, we drew it once before, but would look like this. This triangle would come up here, and then the short one right there. We don't really need to do that though. Let's just do all the areas but keep them positive. So my first area that I did in yellow was 1/2 pi times the radius squared. My second area that we're going to add on is 1/2 the base times the height. And then the third area we're going to add on is 1/2 times the base times the height, adding all of them because we're doing the absolute value. So we go through 4, half of 4 is 2, this becomes 2 pi, half of 36 is 18, and this is 3/2. Okay, that's really fine to stop. You can be an overachiever and go further if you would like. You could say that this is 2 pi plus, and you could give this common denominators 36/2 plus 3/2, which gives us 2 pi plus 39/2, if that makes you feel happier. But you could have stopped at any of those steps I wrote in black there. They are all the same thing. Mine is maybe the most simplified, but don't forget the AP exam doesn't care how far you simplify. All right, 6. Find the value of the integral from 0 to 11 of v of t dt and explain the meaning. Didn't we just do that? Oh, wait, no we didn't. This one had absolute value, this one doesn't. Well, sometimes I'll see people look at this, and I'm going to erase this very next step, so hang tight. They say, oh, fundamental theorem. This becomes x of t, we have to plug in 0, plug in 11. And that's awesome. But if you plug those in, you need to know those values. And so far, they didn't tell us anything about x of t. So I think that's not what we're going to do here. But remember, the other way to calculate an integral is to measure the area beneath a graph. And so we can just do the same areas as before, right? We have 2 pi, we also found 18, and we also found 3/2. However, there is no absolute value here. The 2 pi is the half circle that's above the x-axis that stays positive. The 18, though, is the area of the triangle which is below the x-axis, and then our small triangle is above. So if we wanted to clean this up, 2 pi minus, we can do the same, 36/2 plus 3/2, which becomes 2 pi minus 33/2. Go us. Okay. Last but not least, if the initial position of the particle is given by x of 0 equals 2, find the position of the particle, or find the position of the function, I should probably say the particle, oops, awkward, at time t equals 11. All right, well this brings into play what we learned at the beginning of class today, which means we're going to be using that fundamental theorem of calculus. Very exciting. We're going to have to manipulate it to get our answer. So how does this work? Well, they're asking us about the antiderivative of velocity. They gave us one piece of information and they want another. So it looks like this. We know the integral from 0 to 11 v of t dt. If we take the antiderivative of v, we'll call it x. You can call it anything you'd like. And then you're going to have to substitute in 11, subtract, and substitute in 0. This is the fundamental theorem of calculus. This is our definition. Now, I knew to use 0 and 11 because those were the two inputs that they gave us in the setup for the problem. Look at these three values here. We have one term, a second, a third. Which one of these three are we interested in finding? We want to find the position of the particle at a time of 11. So let's isolate that guy. To do that, we are just going to add x of 0 to the left side. And so we get x of 0 plus the integral from 0 to 11 v of t dt equals x of 11, right? I just added this over to the other side. Great. Now, let's do the math. X of 0 they gave us, that's 2. Very exciting. And I'm going to work down below. I'm just going to say x of 11. We'll switch the order. So we get 2 for that x of 0 plus, then I need the integral from 0 to 11 of v of t dt. Well, what is that? Oh wait, we just found that on 6. How exciting. That is 2 pi minus 33 halves. And then if you wanted to clean this up, we could say 2 is 4 over 2, right? 4 over 2 plus 2 pi minus 33 halves, which becomes 4 minus 33, I think, is negative 29 halves plus 2 pi. Awesome. Now, 2 things to finish up this problem. First, I didn't actually finish with problem 6, because 6 said, after you find the value, please interpret the meaning of this integral. Now, I've found in the past that this becomes a little bit easier if we actually give a decimal value to these. I would not suggest you ever turn this into a decimal value on the test, but at least for today, let's go ahead and look at the decimal value of 2 pi minus 33 halves, right? So we're going to go over here and we're going to say 2 pi minus 33 halves. So negative 10.216. So it's approximately negative 10.216. What does that mean? Well, what it means is we started at some value or at some position at a time of 0. Here's my number line. I don't know where I'm starting. And we'll say that this happened at a time of 0. And then at a time of 11, I don't know where I'm ending up. But what I do know is that I am displaced by 10.216 units because it's negative to the left of where I started. So here I am at a time of 0. By the end, when I've stopped paying attention, I am at a time of 11 over here. Don't know where I am, but I definitely know I'm negative 10.216 units to the left of where I started. Cool. Now, if you wanted to see that visually, what actually happened? Well, I moved to the right a small amount. And then at an x of 4, because my area is negative, now I'm moving to the left a very large amount, a very big area. And then at the end, I moved just a little bit back to the right again. So I walked to the right for a bit, then turned around, walked to the left for a long time, turned around, and walked to the right at the very end. Okay. Well, what did we find down here? Down here, we found the position of the particle at 11. So what they're telling us, and let's find this another approximation, negative 29 halves plus 2 pi, negative 29 halves plus 2 pi, okay, negative 8.216. All right, now I'm going to draw that same number line again, though maybe a little bit more carefully. We're going to put 2 values on here. In particular, we started at an x value of 2. So I started over here at 2, and that occurred at a time of 0. And I ended up, where did I end up? I ended up at negative 8.216. Negative 8.216, and that occurred at a time of 11. Okay? Remember that this value is right here. How did we get there? Well, and this is where this accumulation function comes in. We take where we started, 2, and then we add on the displacement. So we started at a position of 2, and then we figure out how much we're displaced by. We start at 2, we are displaced by this amount, and so now we know where we ended up, at a position of negative 8.216. To go even further, what does this guy up at the top mean? 2 pi plus 39 halves. Well, this is 2 pi plus 39, oops, that's tough, plus 39 halves. Let's try for a 3 this time, Mr. Grant, come on. There we go. 25.783, that's a huge number. What does that tell us about our number line down here? Well, it actually doesn't tell us anything. But if you wanted, again, that same visual from what we did up above, right? We went to the right, then to the left, then to the right. Here's what happened. I moved to the right some amount, and then I stopped, turned around, and I moved, this is the triangle, the big triangle, to the left too far, and then I stopped and turned around and moved to the right just a little bit. And that's what got me to negative 8.216. If you sum up all three of those lines on there, if you sum up the yellow, the red, and the purple, that will tell us the total distance that we traveled. So from a time of 0 to a time of 11, we traveled 25.783 total units. All right, I think that's pretty good for now. So we will come back and I'm going to do a part 2 of this video, and that will take us through the last 2 examples. You will definitely want your graphing calculator for this next one. So thank you so much for tuning in. And again, next class we will do these last 2.